Okay, you know I don't like to move around, but I'm going to have to move around in this case. And let me just tell you what we want to do. I'm going to make a series of videos, and I want to model the motion of a mass on a spring, but as it moves around, and actually in 3 dimensions like that. But the first thing I need to do is build a model for the force due to the spring. If you take a spring and this one's all kinked up, it still works just fine, and the more you stretch it, the greater the force it pulls back this way. So how do I get a model for that? This is what I'm going to do. I'm going to take my spring. I'm going to measure the length of it, L0. And then I'm going to take that same spring and add a mass to it. And it will stretch, M1. So in this case, the forces on this mass are, if the mass is just hanging there motionless, then I have the gravitational force M1G pulling down. I have the spring force pulling up, Fs, and those two are equal. So in the y direction, F net y equals 0 because the change momentum 0. It's just sitting there. So I get F spring minus M1G. So I can also measure this length, L. And then I can add another mass and get another spring force. So I get the spring force equals M1G for that case. And then as I add that more and more, and I can do it again. So I want to collect data that looks like this. The spring force will actually just be the mass, right? The mass, which I can find the spring force from up here. And then let's write this as L. So I'm going to get data, 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 and then I'll do maybe 5 data points. And from that, I can analyze and get an expression for the magnitude of the spring force as a function of S, where S is the stretch, how much it's stretched, equals some function. So we could just write that at S of F equals some function. That's what I want. And that's what I'm going to do. So we're going to move over here, and I'm going to set up an experiment to do this and actually measure it. And then we'll make a graph to find this, and that's what we're going to do. Come over here, we'll do that. Okay, it's me. So I'm going to collect data in real time. Oh, take this off. So I'm going to collect data in real time so you can see exactly what's going on. I have here my spring, and it's mounted to this thing right here. I'm going to go ahead and write down the Y value of the mount point up here. So it's at 47.5, let's say. I'm writing that down. Y0 is 47.5 centimeters. And now the unstretched length is going to be, I'm just going to write down the calculation. So I'm going to count it up to the top of that little ring right there. So that's, let's say, 40.2. So Ly is going to be 47.5 minus 40.2 centimeters. I wrote that down. I'm writing it down. Let's see. I'll show it to you what I have in a little bit. Okay, now I'm going to add some masses. I'm going to start with this one. It's a 20-gram mass. So I'm going to write the mass of 20, and the position is 37. Now I will add another 20. So that's 40. 40, that's 33.2. Let's see, what's this? 50, so let's just take this off and put a 50 on there. And write down 50, and I get, let's see, that's about, I'm not doing a great job because I don't really care, and it's going to work anyway, 31.3. Now I will take this off. Let's do, what's this one? Another 50. Let's do 70. I'll do 70, and then I'll do 100, and then I'll do, I don't know what I'm going to do. 50, so that's 70 at 27.4. Let's do 100. So that's, take that off. Put this on. And then I'm going to, so that's 100. And that will be 20 1.8. Let's do 2 more. I'll do 120. And 120 is going to, I have enough, but let's see. That's going to be 18. And then 1 more, I'll do this 200. That's a 100. Okay, I'll stop there. Okay, so now we need to take this data, which I actually have, see, and make a graph, and that's what I'll do next. Okay, so I have my data. I've already put it in the spreadsheet. Now, I'm using Google Sheets, okay? It's free, and it's great, but I don't like plotting there, so I'm actually going to do something weird. I'm gonna edit these values a little bit and then plot something different. So I have everything. I have the stuff that I wrote down, the initial position of the top, the length, which I've already calculated, the gravitational field G, the masses, the distances. Okay, so let's just calculate. I should have done this. Actually, let me put this up here. Y0, let's just cut this whole thing. Put it up here. So now I can do, let's do the math. I want the force versus S, right? So the force, that's going to be this mass divided by 1,000. Actually, let me put that in parentheses. This mass divided by 1,000, because I need to convert to kilograms, 1,000, not 100, times this gravitational field. And I'm going to put a $sign right there. That means don't change that cell. Okay, so that's 0.196 newtons. I can drag that down like that. Now, and that's in, I put this as F in newtons, even though I don't have to do that. And then I want the S in meters. So what's the stretch? Well, that's going to be this position. I could plot just this position and it would work. But I want to find out how much it has stretched. So it's going to be this position minus the unstretched length minus this. Well, that's the weight, that's 47. So it'd be actually the other way around. It's going to be, I put it in parentheses. So it's going to be equal to the position, which is this, minus this. Is that right? So that would be 10.7. That's how long it is. And then I need to subtract from that the natural length, the unstretched length. I feel like because I got my numbers backwards, I feel like I'm getting this messed up, but let's just do this. And then all of that I need to divide by 100 to get that in meters. Okay, let's see if this works. So why are those negative? That doesn't make sense. So F2, oh, that's because this D2 right here, that's right. But then, oh, F1, that one needs to be a star, asterisk right there, because not a thing. And then I can recopy it. Okay, so then here's my distance, my stretch distance, and my force. So let's just copy this, these values, and now I'm going to graph it in Plotly. So I'm going to switch over here to Plotly. I'm going to click Create a New Chart, and I guess I should have shown the whole thing. I should have, but that's fine. And I'm going to paste it right here, and then I'm going to plot. I want to plot force on the y-axis. So I'm going to go over here to Add Trace, and it's a scatter. The x value is going to be my B column. My y column is going to be my A column. And there's my graph. And actually that goes over more further, and I'll show you in just a second. Now, and I can go over here and say, if I want to do F in newtons and S in meters. Now I can add a best fit line here, so I go to Analyze, Curve Fitting, Add a Fit, select Trace 0, my first one, and I want a linear fit. I have to pick some parameters for A and B, and I run it, and I get a slope. I'm going to write this down because I need it later. I need a slope of 5.156 newtons per meter. And that, see, it's right here. And that is my spring constant K. And there's my graph right there. You see, it's a really nice fit. And I wasn't even being careful. Okay, so that is my K value. Now I just need to write this all down as a model. And I will do that back over there at my paper to finish this off. And then we'll have our model for the force due to a spring. Okay, I'll see you over there. Okay, so I have my rough model to get the magnitude of the spring force. It says that it's equal to the spring constant K times the stretch, and that was because I plotted F versus S. So this is like Y equals mx plus b, where the m would be that. Now, and S is the x and Y is F. So it's just a normal straight line. I did have b close to 0. It wasn't exactly 0, and that's fine. But this just tells me the magnitude of the spring force. I need a vector value for the spring force. So if I do the following, let's say first call this the vector L. From the beginning of the spring to the end of the spring, even if it's stretched, no matter what. And then I have the magnitude of the net unstretched length I call L0. So that means that this distance S is going to be equal to the magnitude of the vector L minus L0. And you'll notice that if the magnitude of L is less than L0, if it's compressed, then I have a negative value for S, so it actually pushes it away. So let me build a vector model for the spring force. If I write it like this, F equals magnitude of L, and I'm sorry, F equals K times the magnitude of L minus L0, that's my stretch, times, I have to make it into a vector again, so I'm going to say times L hat. So L hat is the unit vector in the direction of L. Let's just make sure that this thing works, right? Because let's say I pull this spring down. I know that the force should be pulling up. So here I have L minus L0 is going to be a positive number. But L hat's down, and I want the vector to be up. So I'm actually going to have to add a negative sign right there. So this means that the force due to the spring is in the opposite direction of the stretch. But I can now model the motion of a spring with that force. And that's what I'm going to do in the next video. I want to take a mass and displace it so that it oscillates up and down and model that motion with a numerical calculation. And we'll do that in the next video.